Okie doke. So, back to our search for a workhorse model. We started with limits to growth, which failed to include economic mechanisms, was extremely inflexible and extremely pessimistic about the future. Then we went on to the DHSS model, which sort of went in the opposite direction, basically, and assumed away depreciation of man-made capital or human-made capital. And then we could even get, and had this very flexible Cobb-Douglas production function, which then told us that we can even get long-run sustainability even if we're totally dependent on non-renewable resources, and even if there's no technological progress. By eking out, we can eke out more and more output from ever smaller flows of non-renewable resources in that model. It was all very fun math, but didn't make a lot of sense when you took it to the data and think about reality. Then we looked at the DICE model, a very early integrated assessment model for climate change, also built on the neoclassical framework, focus on pollution, not resource use. There's no resource use in the model, and because of that it ends up being very abstract. We have these sort of abatement cost functions and things which we don't know where they come from. Surely we want to include both resource use and pollution in the same model, right? So let's have a look at one model that just about does that, and that's another sort of integrated assessment model, which is Acemoglu et al. 2012. Note that the focus of Acemoglu et al.'s paper is the role of research subsidies and technological change in dealing in climate policy, basically. It's not sold as an integrated assessment model. But our focus is not on research subsidies and so on. Here, our focus is on the workhorse properties, the properties of the model, the structure. Is it a good workhorse? Is it a sensible structure? Okay. So here's the structure, and sorry, I'm just going to pause here. Okay, I changed the slide format slightly, which made it didn't fit into my video window here. Okay, so here's the structure. Super complicated, and as you can see, it's no longer fitting the neoclassical picture at all. Okay, so this is gonna be hard work here. We need to get our heads around this. So let's just, before I start flicking through these equations, let's just try and get the overall picture. So we've got households supplying labor, which can go to two places actually, and the labor types of labor are distinguished. This is ordinary labor, so to speak. This is research workers, of which there's sort of a unit mass. So this is the research sector, and this is the production labor. Research labor can either go into research on the dirty good or the clean good. Production labor can either go into production of the dirty good or the clean good. Here's output of the dirty good and output of the clean good, which then get, in this box, they get combined into an overall output. This overall output can be consumed, or it can be used, recycled as a set of intermediate goods that are used in production of the clean good, or it can be recycled as a set of intermediate goods used in production of the dirty good. Okay, so this is a kind of a Roma kind of framework. Hopefully you remember the Roma model. Okay. So then these intermediate goods, they show up in the production function here, right? I've simplified this, but xd here, psi xd is the total quantity, so y is equal to psi xd plus psi xc plus c plus cqr. So that's the inflow and the outflows. So psi is just a parameter. xd comes in here and gets divided into these different intermediates, but I'm not showing that in these equations. In the end, it boils down to this, that production yd is ld to the power of this lot, ad, which is productivity term, to the power of this, xd to the power of alpha 1. Okay, where xd is like essentially the quantity of the intermediate. And similar here, but a bit simpler, because on the right here for d, we're also using this non-renewable resource, R. Okay, if we set alpha 2 equal to 0, this one looks basically the same as this one. And actually in most of the paper, Acemoglu et al., they set alpha 2 equal to 0. If alpha 2 is not 0, we also need this non-renewable resource as an input, which has to be extracted, and there's an extraction cost, which is this. Okay, so that's the broad outlines. Let's see now. We'll do it all again briefly with the help of these red highlighting. So this is labor. This is the production of the final goods. This is where the final good goes, either recycled or used in extraction or consumption. This is technological progress, which is a linear function of the labor inputs SC and SD. Consumption, natural resources and damages. Okay. And crucially here, it turns out you might think, oh, here emissions are linked to natural resource use. But actually they're not, or not directly anyway. In most of the paper, Acemoglu et al. Set alpha 2 equal to 0, so this whole natural resource sector drops out completely. And we just assume that this product is somehow dirty, whereas this one is clean. And the more of it we produce, the more emissions there are. Okay. If alpha 2 is greater than 0, then we need this flow R to produce the dirty good, but still emissions are not linked directly to the flow R, they're linked to the production of the dirty good. So what this does is that if R starts to drop because this is running out, that's like good news, because it restricts the production of the dirty good. So by adding this alpha 2 greater than 0, we have the potential of this resource running out to prevent production of the dirty good. But there's still no direct link between fossil fuel use and emissions. Okay. Utility is a function of consumption and the state of the environment, basically. So is there a physical link between natural resource use and emissions in the model? Not really. How do we stop emissions in this model? Okay. You might want to pause the video and think about that here. If we want to stop emissions, how do we do that? Well, it's pretty clear actually, isn't it? Emissions are just equal to YD, so to stop emissions we just have to stop producing the dirty good. which means if we're not all just going to stop production altogether, we have to shift to the clean good. So that's what we would call a composition effect in the pollution decomposition literature, right? We're changing the composition of production and consumption away from dirty goods and towards clean goods. But the pollution decomposition literature tells us that in practice, in cases where we have massively cleaned up pollution, it hasn't been through changes in composition, it's been through changes in technology. Like, how did we stop emitting lead to the air? We didn't stop driving cars, we stopped adding lead to petrol. How did we stop emitting CFCs to the air? We didn't stop using fridges, we stopped putting CFCs into the fridges, etc. Okay. So the key method for adaptation in this model is not the method. Well, in fact, the only method for adaptation in this model is not the key method that we see in reality. So this is obviously a huge problem. Compare it to DICE. How did we stop emissions in DICE? Well, then it was this abstract end of pipe abatement, wasn't it? We had this, we put resources, diverted final goods away from consumption and investment and into abating emissions at the end of the pipe. Okay. So in neither case are we really thinking clearly in physical terms about where the emissions are coming from and how we can change things around. If most emissions came from cattle, would this composition effect assumption make sense? Well, it might do, right? Because there it seems like, at the moment anyway, we lack technologies to keep eating beef and drinking milk and so on and not have these large methane emissions and so on and other environmental problems associated with cattle raising. So we need to get rid of those emissions, we need to shift out of those products, right? We need to shift from the dirty sector to the clean. But that's not a trivial sector, but it's quite small in the global context, right? And all the rest of emissions, all the fossil emissions that are the core problem for climate change, they are coming from we need a different analysis to capture those and to think about how to get rid of those. Okay. So what role does the natural resource play in this model? Oh, sorry, that's my pen, I'm mucking around here. Well, not a lot really. They're not the source of pollution. A lack of natural resources could potentially break emissions of pollution, slow down emissions by slowing down production in the dirty sector. That's it. Is this a good workhorse to build on for general analyses of natural resource use and pollution, emissions, and potentially biodiversity and so on? Definitely not. Okay. And that's the end of that. And for the final main video, we're going to look at the Golosov model, which we're going to find makes a lot more sense. If you're wondering whether I'm ever going to get to a model that I actually like, it's coming up.